Welcome back, students. Now in today's session, we will learn scheduling criteria as well as scheduling algorithms. While scheduling, we need to place certain criteria for selecting the suitable scheduling algorithms. So different CPU scheduling algorithms may have different properties. The choice of a particular algorithm may favor one of the class of process over another. So here, while choosing a particular algorithm, it may give you best performance for a certain class of processes, while it may not perform well over other class of processes. So we have to be very particular while choosing an algorithm. So here, we need to place certain criteria to examine the performance of the algorithm. So first criteria here is CPU utilization. It is the amount of time that the CPU is busy executing a process. So what percent of time is given for the CPU to utilize it in a best way. That means a process is under execution, we will consider that time here. It includes CPU utilization. Second thing is throughput. This is the number of processes that are completed per unit time. So throughput means how many number of processes we are able to complete their execution in a given unit time. Next is response time. It is the amount of time it takes from when a request was submitted until the first response occurs. Now, this does not include the output time for the entire process. This is only the response time. It means that when you have submitted, when a process is submitted for its execution, and from this time till the time it has been given the processor, the response has been given for the request. This is the response time. Next is waiting time. The amount of time before a process starts after first entering the ready queue. This is the amount of time the process spends in a ready queue when it is first inserted in the ready queue. That is the sum of the amount of time a process has spent waiting the ready queue. Next is turnaround time. This is the amount of time taken by a process to execute from the time it was submitted through its entire completion. So turnaround time, you'll calculate this time from when it was submitted to the processor, right? And the time it has completed its execution. So this will give you turnaround time. So here we need to place these criteria: CPU utilization, throughput, response time, turnaround time. Now here we have optimization criteria. Now all of these criteria we have placed. Now we will focus on these criteria. Some of the criteria we need to maximize and some of the criteria needs to be minimized here. So it is desirable to maximize CPU utilization, throughput, whereas turnaround time, start time, wait time and response time should be minimized here. So in most cases, we strive to optimize the average measure of each metric. In some of the other cases, it is more important to optimize the minimum or maximum values rather than the average. Now we'll look towards single processor scheduling algorithm. Now here, a stress is given on single processor where you have one and only one processor which is being scheduled among the processes in the system. Now there are 4 algorithms for single processor scheduling. First come first serve. that is FCFS, shortest job first, priority scheduling, and round robin scheduling. We'll see it one by one. First come, first serve scheduling. Let us understand this with the help of example. Now here you have certain values given here. You have a chart showing you a process and burst time. By burst time we mean the execution time taken by the process to complete. Burst time means the time taken by process to complete its execution. So here we have three processes labeled as P1, P2, P3 and their respective burst time as 24, 3 and 3. Now this will be in milliseconds. Now with this first come first serve scheduling, the processes that request the CPU first will be allocated the CPU first. Whichever process requests for the CPU first will be given the CPU first. Now here we have case 1. Now consider that the processes arrive in order. Now the same chart we are using here, same table we are using, and we are assuming that these processes arrive in the order that P1 arrives first, then comes P2 and then comes P3. Now looking at the order of arrival, we try to create a Gantt chart, and it is important here. Now how Gantt chart will be created? At time 0 there were no processes, so whichever process request first, here in our example we have P1 requesting first and it came first, it arrived first. So from 0 milliseconds to the time of its execution, we will draw a chart showing the time for complete this particular section for P1's execution. Then after P1 came P2 and its burst time is 3. So P2 will begin at the time P1 finishes the execution. So right from here at 24, the execution of P2 begins and will execute for 3 milliseconds. So hence we calculated here after 24, we calculated 3 milliseconds. So it is now 27. Then comes here P3, process P3, and its burst time is also 3 here. But the time it arrived is now 27. So from 27 onwards we'll calculate 3 milliseconds, and this is the total slot of execution for process P3. This is how we create the Gantt chart here. Now based on this Gantt chart, we'll try to find out the waiting time, average waiting time and average turnaround time. See here, P1's waiting time is 0. Okay, P2's waiting time is 24 and P3 waiting time is 27. Looking at this waiting time, we try to find out the average waiting time. So average waiting time, just sum up all these three since we have three processes. So add the waiting time for individual processes together and divided by the number of processes. You will get the average waiting time as 17 here in this case. Now we'll try to find out the turnaround time. The turnaround time is the time when a process has finished its execution. So in case of P1 it is 24, right? And in case of P2 it is 27. P3 executed at 30. So we will add up these three values and divide it by 3 to get average turnaround time. So here we got waiting time as 27, average waiting time as 17 and average turnaround time as 27. Now we have another case to discuss here. Suppose that the processes arrive in order P2, P3 and P1, exactly reverse of the first case. So the order of arrival here for the processes is P2, P3 and then P1. Since P1 is taking the longest execution time, let us draw a Gantt chart. I hope here you have understood how to draw a Gantt chart. So P2 arrived first and its burst time is 3 milliseconds. Hence, it will begin at 0 and will execute till 3 milliseconds. Then came P3. So P3 will begin at 3 milliseconds and will execute for 3 milliseconds more. Now P1 will begin at 6 and will execute for 24 milliseconds. Now we try to find out the waiting time. So P1's waiting time is now 6, P2's waiting time is 0 and P3's waiting time is 3. If we try to find average waiting time, look at here. In case here we are getting much lower value, right? So if we compare it with case 1, which was 17, right? So comparatively it is very much less here. And optimization criteria, we have met one optimization criteria to minimize the waiting time, right? Then we try to find out the average turnaround time, whereas in this case it is 13. In earlier case we saw that it is 27. So the order of arrival also matters here a lot in minimizing the waiting time and average turnaround time. Now case 1 is an example of conveyor effect. All the other processes waiting for one long process to finish using the CPU. The conveyor effect is an effect where you have one long process running while all the other processes, they are waiting to finish the long process execution. This problem results in lower CPU utilization as well as device utilization. So case 2 shows that the higher utilization might be possible if we have short processes that are allowed to run first. Now FCFS scheduling algorithm is non-primitive. It means that once the CPU has been allocated to a process, then the process keeps the CPU until it releases it, either by termination or by requesting an IO operation. It is a troublesome algorithm for time sharing system. So this particular algorithm is not suitable for time sharing system because it is non-primitive. Once you have allocated the CPU, the process will keep the CPU till its termination, or that means you cannot forcefully take back CPU from the allocated process. Next scheduling algorithm is shortest job first, a well-known SJF scheduling. Now, as the name indicates here, this algorithm associates with each process the length of its next CPU burst. It is based on the length of the CPU burst. When the CPU becomes available, it is assigned to the process that has the smallest CPU burst. So in case of FCFS, we used to allocate whichever process comes, the CPU will be allocated to that process. But now here we will examine the CPU burst of the processes, and then we'll find out the smallest CPU burst process, will allocate the processor to it. Now there are two schemes here in SJF. Non-primitive, where once you have allocated the CPU, you cannot take it back. You cannot interrupt in between. You'll have to wait till the process completes its execution. We have another option here, that is primitive. So in this case, if you are adopting shortest job first, in case of primitive scheduling, if a new process arrives with the CPU burst length less than the remaining time of the current executing process, then we will preempt. That means we will raise an interrupt here, and then will switch from this current process to the new process whose burst time is smaller than the current executing process. And now this case is also known as shortest remaining time first. Let us understand this with the help of an example. Now here we have four processes in the system and their arrival time is 00, and their burst time is also given here. So in case of P1 it is having burst time as 6, P2 has burst time 4, P3 is having 1, and P4 is having burst time as 5. Now looking at this table, we come to know that P3 is the smallest among the processes whose burst time is smallest. Now in case of non-primitive scheduling, as all of the processes have arrived at the same time, we can switch to process P3's execution first. Okay, so P3 will execute first, then P2, because it is the next, its first time is the next shortest one, then P4, and lastly will execute P1. Calculating the average waiting time will give you the value of 4. Now looking at this Gantt chart only, we will find out the average waiting time. So in this case it is 4. There is average turnaround time. Here you can see it is 8 milliseconds. So in case if it is non-primitive and they arrive at the same time, all of the processes are available at the same time. Now in case of non-primitive scheduling where the arrival time varies, so at time 00 we do not have any other process in the system, so we'll have to start the execution of P1 only, whereas its burst time is quite big. So the processor will start executing process P1, but at time 2 there comes in process P2 whose burst time is less than P1. So till time 2 P1 will execute, and after that, but see here in this case it is non-primitive. So once the process has been allocated to a processor, you cannot forcefully stop its execution. So we'll have to execute P1 first, even though it is having longest burst time. Okay. Now after that, by the time P1 finishes, all the other processes are in the system. So here we can take advantage of this and we can choose among the process to execute next. So from this, because P3 is the smallest one, we will execute it first after P1. Then we have a choice here. We do have a choice for P2 and P4, but whose burst time is conflicting. They have the same burst time. So in that case, to resolve this conflict, we can look over the arrival time. Looking at the arrival time, we come to know that P2 came first, so we will switch to P2 after P3. And then lastly, we'll execute P4. Then we'll try to calculate here waiting time using this Gantt chart. Hence, the average waiting time we are getting in this case is 4 and average turnaround time is 8. Now in case of primitive scheduling, we are considering the same example and their arrival time as shown here. But now here in this case we can stop the execution of P1 and we can switch to the shortest burst time process, right? So here at 0 time P1 will start its execution. At time 2 we have an option as P2 in the system whose burst time is less than P1. So processor will be allocated to P2 here. Okay. Then P2 will execute. At time 4 we are having P1 whose burst time is less, right? P2 requires 4 milliseconds. Okay, so by the time it completes, we have P3 in the system available, whose burst time is shorter than P2. So processor will be allocated to P2 here. I'm sorry, P3. Then P3 will execute and the remaining burst time for P2 will be completed. Then at time 5 we have P4, whose burst time is even shorter than the P1. So here P4 will execute and lastly P1 will complete its execution. Looking at this Gantt chart, we found that the average waiting time in this case is minimized to 3 and average turnaround time is 9.75. Next scheduling algorithm is priority scheduling. Like SJF is a special case of general priority scheduling algorithm. In SJF also we gave priority to the smallest burst time. So some criteria we placed here. So we can consider this SJF as a general priority scheduling algorithm. Now a priority number is, that is an integer number, is associated with each process. In priority scheduling, we have a priority number associated with each of the processes. The CPU is allocated to the process with the highest priority. Now we can assign smallest integer number indicating as highest priority. The priority scheduling can either primitive or non-primitive. In case if it is primitive, then prompt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. In case if you are adopting priority scheduling, that too of type primitive, you can approach while preempting the CPU if there comes a new process who is having a priority higher than the current process. In case of non-primitive, we'll simply put the new case at the head of the ready queue. That means you cannot switch from the current process to the new process even though it is having the highest priority. But one thing we can do is we can place the new process whose priority is higher than the current one at the head of the ready queue. So SJF is a priority scheduling where priority is predicted next CPU burst time. The main problem with the priority scheduling is starvation. Now starvation means it may happen that a lower priority processes may never execute. If all time there comes a new process whose priorities are higher only, then the turn of the lower priority process will never come. So this problem is called as starvation. Now the problem of starvation can be solved by aging. Now aging, as the time progresses, the priority of a process in the ready queue is increased. See, all the ready processes, all the processes those are ready for the execution are placed in the ready queue, and also their priorities are also associated with it. Now here, if we want to solve this problem of starvation, we can adopt aging. Aging means as the time increases, as the time progresses, the priority of the processes that are waiting in the ready queue, we are increasing their priorities. Okay, this is called as aging. Now next algorithm is round robin scheduling. In round robin scheduling, each process gets a small unit of CPU time. Now this small unit of CPU time that we are allocating to each of the processes turn wise is called as a time quantum. Now usually the time quantum is 10 to 100 milliseconds. Now after this time has elapsed, the process is preempted and added to the end of the ready queue. So in round robin, there comes a turn of every process, and the process is given the CPU for this time quantum only. If it finishes in this time quantum, it's okay. If it doesn't finishes, then also it has to release the processor, and it will be added at the end of the ready queue. Now if there are n processes in the ready queue and the time quantum is q, let us consider the time quantum as q for a general notation. Then each process gets 1/nth of the process time in chunks at most q time units at once. That means if you are having n number of processes, right, and the time quantum you have taken is q, then each of the process will get at most 1/n CPU time in chunks of at most q time quantum. Okay, and no process waits more than n-1 q time quantums. Now the performance of round robin algorithm depends on the time quantum here. If you are taking the time quantum as large, then it will give you performance similar to that of first come first serve scheduling algorithm. Now in case if you are selecting time quantum small, then the time quantum you are selecting must be greater than the context switch time. Otherwise, you will face the problem of overhead. Okay. One thumb rule that is applied here is 80% of CPU burst should be shorter than the time quantum. Whatever time quantum you are selecting, 80% of CPU burst should be shorter than that. Let us understand this with the help of examples. Now here in this case, the time quantum we have selected is 20 milliseconds. Now here we are having number of processes P1, P2, P3 and P4, and their burst times are given here. We try to create a Gantt chart. Right, we try to create a Gantt chart. Now as time quantum is 20, P1 will get 20 milliseconds even though it doesn't complete in this 20 milliseconds. Then there comes the turn of P2, will get 20 milliseconds as well, but it finishes before that because its burst time is 17. Then time quantum is given for P3 and it will execute for 20 milliseconds, and then for P4 will execute for 20 milliseconds. Then again, as the remaining time of P1, P3 and P4 is there, will give 20 milliseconds to each of these processes. If they complete it, well, if they doesn't complete, then they'll have to wait till their turn comes. So here, typically high average turnaround time than SJF. You are getting higher turnaround time as compared to shortest job first, but you are getting better response time here. Okay, because the processes do not have to wait for one long process to finish its execution. Okay, so all of the processes are treated equally here. Now calculating the average turnaround time, we are getting it as 73. Sorry, average waiting time we are getting it as 73 and average turnaround time as 113.5 milliseconds. Now the time quantum and context switch. Context switch we have discussed it earlier also, where you switch from one process saving their current state over the stack and loading another process and executing the next process. That means you are allocating CPU to the next process. So this is the context switch, right? So the time it takes to while doing all of these things is called as context switch time. So time quantum should always be less than the the context switch time quantum should be less than that. So here if you are having process time as 10 the and time quantum is 12, that means you are having a process whose execution time is 10 milliseconds and you are keeping time quantum as 12, there will be zero context switch. If the process time is 10 here but time quantum you have selected as 6 millisecond, there will be one context switch. And in case you have taken time quantum as 1, see those many context switch will be there. Okay, so 9 context switches will be there. So it is very important to carefully select the time quantum to avoid context switching and additional overhead. Now this graph shows you average turnaround time that varies with the time quantum. See here process 1 whose time is 6, process 2 whose time is 3, process 3 whose time is 1, and process P4 whose time is 7. So average turnaround time of a set of processes does not necessarily here improve as the time quantum increases. If you increase the time quantum, the average turnaround time of these processes doesn't improve. So in general, the average turnaround time can be improved if most processes finishes their execution in single time quantum. Now, I hope you have understood today's topic. So we will stop here. Till then, we'll meet in the next lecture. Till then, take care.